time change, cause our minds change and what we think is good. I wasn't raised.
Hello guys, this is the question about our project, and this is the equation. First we have y double prime minus y up to 3 and plus a y equals to 0. And in this case we have the initial value, which is v y equals to 1. And then the first equation is, first we need to plot some trajectories and at a positive, a negative, and a 0 with the parameter of a. In this case, we need prove the numerical method and compare with the improved that coming from Euler method and Krumé-Kuta method. And the second question, we have equilibrium and classify to know about the stable and the stable of equation itself. In the third, we have y-phase plane plot corresponding to positive and negative value of parameter of a. And the last is y0 deserves to be called the critical value of parameter of a that coming from equation 1.
Hello, this is the equation from the given question, and this is the initial value problem. So here we set the v dv over dy minus y power of 3 plus ay equal to 0, and then we put this dy to the right side and also the y power of 3 and plus ay, and then we integrate this part and this part reflect from the dv and dy, and we found this another one equation, and v power of 2 over 2 equal to this one, and we should change this one to this form, so we decided to times by 2, and we found that c equal to 1, and we move to this one, or we replace 1 as the c, and then here we found that v equal to square root of y equal to 4 over 2 minus ay power of 2 plus 1, and we have to set 3 parameter, which is positive, 0, and negative. So we decided to pick 1, 0, and minus 1, and then the final equation is v equal to square root of y power of 4 over 2 minus y squared plus 1 for a equal to 1, and then for a equal to 0, here this equation v equal to square root of y to power of 4 over 2 plus 1, and for a equal to minus 1, v equal square root of y the power of 4 over 2 plus y squared plus 1.
So here we have 3 cases. First is when a equal to 1, second is when a equal to 0, and the last is when a equal to minus 1. The y represents x and the v represents y. So here we can see the difference between these 3 formulas, this one, and this one. So here we come up with this result. This is the analytical or the exact result. This is when a equal to 0, when a equal to 1, and when a equal to minus 1. So here's with the increment 0.05 from the range 0 to 0.5. 1.
So for the second question, we have to find the equilibria and classify as the stable or unstable. If for this second order questions. So we have the py as minus y to the power of 3 and plus ay equal to 0. So we can derive it such thing like this: y bracket open bracket minus y square plus a close bracket equal to 0. So we have three cases when the y become first when the y become y equal to 0, and the second when y become square root of a, and the last is when y become the minus square root of a. First, we have now that we have equations in equilibria which is py greater than 0, and we decide the interval from the negative 10 until 10. First, the y equal to 0 is less than y and less than b, and we choose y as 1, and the equation become minus y to the power of 3 plus a y, and we put 1 in the functions which is becoming minus 1 plus a. This is for py greater than 0. If a is greater than 0, we choose 2, minus 1 plus 2, it will become 1. So 1 is greater than 0. Is it right? So a greater than 0 will be stable, and the otherwise which is a less than 0 become unstable. This is also applicable in the py less than 0. We choose a greater than 0 will be stable, and a becomes 0 is unstable in the form of equilibrium in y equal to 0. This is the first case. And the second case, we have y is equal to square root of a. We decide to a become 1. We derive this equation from the formula square root of a less than y less than 10. So we choose y equal to 2, and we put in the py and become py is less than py is negative 6, and this is from py greater than square root of a. Then we know that a is a 1 and a become 1, and we have py minus 6. So negative 6 is greater than 1. Is it not correct, right? So the square root of a is unstable. And the last case, when y is minus square root of a, we decide py is less than minus square root of a. First, we choose a as 1, and we derive this formula from the general form, which is this minus 10 less than y less than minus square root of a. We choose y as a minus 2, and we put the minus 2 into the py, which is become 6, and the py is less than minus 1. Is it not correct, right? So it is also applicable for those two minus square root of a and minus square root of a, which is unstable.
So relate to question number 3, y best plane plot corresponding to positive and negative value of parameter of a. So we have 3 pairs of the line, which is red, green, and purple. In the red case, we have a greater than 0, and in the line of green, we have a equal to 0, and in the purple line, we have a smaller than 0.
That is why the phase plane corresponding to the 3 graph here, the red and the green and the purple.
So, as we related to the number 4, which is why the 0 is called by critical value, as we know, the question is minus y to the power 3 and plus ay, and we can separate it like this, and we get a value of y. First y is 0, then second y is plus minus the root of a, which is we can differentiate it to this root of a and minus root of a. And if we put the a in 0, the answer of first y is 0. the answer of the second y, if we put a 0 here, it will be 0 also. And the third y, we put 0 minus times with 0 will be 0. So that's why the critical value 0 is called by critical value. And second is from the graph. As we know that the graph is a break in the 0 point, and this is actually the implemented of the formula before. So next is our numerical method for our question. First, we use the Runge-Kutta method, which has this formula, and we go to the table itself. So the table itself, we have three parameters of A, which is -1, 0, and +1. In the -1 and the third table, the three table, we use a different H, which is this table. It has a 0.05 H, and this table, the smallest one, is using 0.1 H. And next, we use also the Euler method, the improved Euler method. The improved Euler method use this website, which is improved Euler Hund's method calculator, and we go to the table, and this is the answer. We use three different A also, -1, 0, and 1. And the H, we use the same H, which is 0.05 and 0.1. And after we calculate, we found some behavior of these two methods.
So we can conclude for these all questions. First, we take one data from the Runge-Kutta. First, we have A equal to 0, and we take the Y equal to 0.5. The phi will be 1.01551. And from the improved Euler methods, as A equal to 0, and we take Y equal to 0.5, the phi will be 1.015659. And from the Runge-Kutta, as A equal to 1, we take Y equal to 0.5, the phi will be 0.883884. And from the improved will be phi equal to 884066. And the last one, A equal to -1, we take the Y equal to 0.5, the phi will be 1.13192. And for the improved Eulers, will be 1.132069.
So here is the analytical method or the exact method, which results exact value. There are three conditions, which is when A equal to 0, A equal to 1, and A equal to -1. When A equal to 0 and Y equal to 0.5, the phi will be 1.01550. And when the A equal to 1 and the Y equal to 0.5, the phi will be 0.883883. And the last is when the A equal to -1, the Y will be 0. The Y is 0.5, the phi will be 1.131923. This analytical method has the nearest value with the rank Runge-Kutta compared to improved Euler's method. Here we are from Laplace. Thank you for your nice attention. Thank you!